Good afternoon and welcome to this special edition of WARF Essential Topics. My name is Laura Heisler and I am Director of Programming for the Wisconsin Alumni Research Foundation, or WARF, and the Director and Co-founder of the Wisconsin Science Festival. Today's talk is a keynote for both the Wisconsin Science Festival, now in its 10th year, and the Alliance for the Arts at Research Universities, or A2RU, annual conference, entitled Land and Equity, the Art of Politics of Place. Both of these endeavors celebrate the centrality of science to a healthy society, and both aim to foster a wide-ranging dialogue on how to forge connections between the public and the basic scientific research enterprise. So we could not be more thrilled to be featuring today's speaker. Before I turn the virtual podium over to the leader of one of our Science Festival partners to offer some opening remarks, I do want to take care of a few logistical details for today's session. I want to start by thanking all of the sponsors of the Wisconsin Science Festival, with a special thanks to gold sponsors Alliant Energy Corporation, Promega Corporation, PBS Wisconsin, and Wisconsin Public Radio, as well as our silver sponsors, American Family Insurance and Thermo Fisher Scientific. I also want to thank the organizers of the festival, WARF, the Morgridge Institute for Research, the Wisconsin Institute for Discovery, and UW-Madison. You can find information on more than 100 events taking place through the rest of this weekend at wisconsinsciencefest.org. We will be holding a Q&A session following Dr. Crim's remarks, and we encourage you to post your questions at any time using the Q&A function in your toolbar rather than the chat today. You will find that in the toolbar if you mouse over it. Today's session is being recorded, and the recording will be available both at warf.org and discovery.wisc.edu. And with that, I would like to turn the virtual podium over to a major visionary in forging creative connections between science and society, Joe Handelsman, Director of the Wisconsin Institute for Discovery.
It's my pleasure to introduce Dr. Fleming Crim, who is our keynote speaker for today. Dr. Crim is currently the Chief Operating Officer at the National Science Foundation and Emeritus Professor here in the Chemistry Department. Before going to the National Science Foundation, Fleming was a faculty member here for 40 years, during which time he was a well-known chemist and was recognized by the American Chemical Society, the American Physical Society, the Royal Society, as well as becoming a member of the National Academy of Sciences and the American Academy for Arts and Sciences. It's a real pleasure to have Fleming back in Madison, even if it's just virtually. He's been a good friend to our campus and a great friend to me, and welcome, Fleming. It's my...
Well, thank you very much. Let me share my screen here. And let me say what a pleasure it is to be back in Madison, even if I am there virtually. A long time ago when Joe asked me to give this talk, I thought it was going to be a trip to Madison at one of the nicest times of year, but of course it's not turning out that way. I want to talk to you today about NSF and particularly NSF's broader impacts. I want to thank the Wisconsin Science Festival and the Alliance for the Arts and Research Universities for arranging this event. And in particular, I wanted to do something that the Alliance asked me to talk about, which is about how the broader impacts program at NSF has consequences for arts and fostering the benefits of basic research. So I'm going to talk about three things. I'm going to talk about how NSF works. I'm going to talk about the broader impacts at NSF. And I'm going to talk about images and arts and how these images convey the meaning of science and how arts can connect to science. This is our building, our new building of NSF. It's not as dramatic as the Wisconsin Institute for Discovery, but you can see here a statement of the mission of NSF. The mission of NSF is to promote the progress of science, to advance the national health, prosperity, and welfare, and to secure the national defense. That language is actually in statute. That's what defines, that's the Organic Act, that defines the National Science Foundation. I want to talk a little bit about how that actually plays out as we look to the future. Here's an interesting statement. It's a statement about basic research. The mission of the foundation is to support basic research. And this statement says basic research provides scientific capital. Today, it is truer than ever that basic research is the pacemaker of technological progress. Now, I don't think any of us would argue with that notion. It seems like it has to be the case. And this very current notion isn't an idea that someone said last week in Forbes or something. It is, in fact, a statement from Vannevar Bush in Science, the Endless Frontier. He wrote it in 1945. The National Science Foundation was founded in 1950, post-World War II, and there was a very intense debate between about 1945, when he wrote this book, and 1950 about how we would fund science and research in the United States. Science had played an incredible role in the war, and the question was, what was the nation going to do going forward? Vannevar Bush, who had been an advisor to President Roosevelt and was a leader in the scientific and defense establishment, was an active participant in this debate. And 5 years after he wrote this statement in Science, the Endless Frontier, the National Science Foundation was founded. So the National Science Foundation is in fact celebrating its 70th anniversary this year. But there's an important point here about basic research being the pacemaker of technological progress. That has been an organizing principle for much of the federal government's funding of scientific research over the years. We've had a leadership transition at the National Science Foundation. France Cordova was the director from 2014 to 2020, one of the few directors in the last several to serve her full 6-year term. And this summer, Sethuraman Panchanathan from Arizona State University became the next director of the National Science Foundation. So Panch, as everybody calls him, is at the foundation and is doing very, very well and really pushing us forward. And he has a very well-articulated vision of the foundation. In fact, one of the things that Panch talks about in his vision of the foundation is it's resting on 3 pillars. These 3 pillars are advancing the frontiers of research, ensuring accessibility and inclusivity, and securing the global leadership of the nation. These 3 pillars rest on a basis of partnerships, and they are tied together by the notion of innovation. The notion of partnerships and innovation allowing us to translate the fruits of fundamental research into improvements for society. Now, NSF funds all fields of science and engineering. The biological sciences, engineering, these are the 7 research directorates of the foundation. The one in the biological sciences, one in engineering, which funds all the areas of engineering, mathematical and physical sciences, computer, information science and engineering, geosciences and polar programs, education and human resource, where many of our diversity and inclusion programs sit, as well as our education research, and the social, behavioral, and economic sciences. I led the directorate for mathematical and physical sciences for 4 years. It contains astronomy, chemistry, materials research, mathematics, and physics. In addition, there are 2 offices that are very important for the research functions of the agency. One is the Office of Integrated Activities, sort of an incubator where we start a lot of new ideas and where we pull a lot of ideas across the foundation together. And the Office of International Science and Engineering, which is the vehicle by which we make a lot of our international connections. So these directorates and offices are where we actually fund the science and engineering research. Where NSF is unique It's unique as a science funding agency in that it funds research across all aspects of science and engineering, except for the biomedical sciences. Let me show you some numbers. Over 90%, 92, 93% of the $8.3 billion budget that NSF received in fiscal year 2020 goes out the door to fund science and engineering, goes out the door to fund research. That was in response to 41,000, well, more than 40,000 proposals, some years as many as 45,000 proposals that the foundation receives. That funding went to 1,800 institutions in over 11,000 awards and touched over 300,000 people. That ranges from principal investigators to graduate students to postdocs to scientists working on projects to K through 12 students and undergraduate students who receive NSF support or are part of an NSF project. About $1.2 billion of that goes to STEM education. About 100 million of it sees public-private partnerships. And as of last week, 248 Nobel laureates had been supported by the National Science Foundation at some point in their career. Over the last couple of weeks, the prize in chemistry, the 3 prizes in physics, and the 2 prizes in economics all went to people who had, some of them still, been funded by the National Science Foundation. So what does that $8.3 billion do? Well, the National Science Foundation supports academic basic research. It provides 27% of the total federal support in all areas of science and engineering and medicine. You can see that in some areas like computer science, it's the dominant player. It provides 83% of the support to academic computer science. Almost 70% in biology and the social sciences. And you can see even in engineering and physical sciences, where you think of other agencies playing a big role, National Science Foundation provides almost half the funding for the academic basic research. Let me take a minute and look at some of these numbers a little differently. In particular, I want to talk about how that $8.3 billion gets turned into 11,000 awards that we support. The process is the process of merit review. Many people say, and we consider the merit review process at the National Science Foundation to be the gold standard of merit review. The merit review criteria are 2, intellectual merit and broader impacts. The National Science Board that oversees the National Science Foundation established these as the 2 organizing principles for the merit review process. Intellectual merit is the potential to advance knowledge. That's what we often think of when we think about research. Broader impacts is the potential to benefit society and contribute to the achievement of specific societal outcomes. The intellectual merit criterion is easy to think about. We're used to thinking about what does a piece of research do in terms of intellectual content and creating new knowledge. Broader impacts is in fact a little more vague and subject to many more interpretations. And that's in fact something I'm going to come back to and talk about more a little bit later. Let me briefly talk about merit review in terms of intellectual merit and broader impacts. Let me talk about the process by which we end up sending support out to a researcher to conduct research. It all begins with a proposal, a bright idea, and a proposal that a principal investigator sends to the National Science Foundation. That undergoes review. A program officer is usually one, sometimes a collection of program officers are responsible for shepherding that process, that proposal and evaluating it. Generally, the program officer assembles an external review panel of experts in the area. The program officer may ask for individual reviews, so-called ad hoc or mail reviews. And what the program officer is trying to do is to build a portfolio of research. The evaluation process, the review process, ends up making a recommendation to the program officer, who looks at the portfolio that is the goal here, and decides what research to fund. The program officer does that by making a recommendation, and that recommendation then goes to the division directors, the next level of oversight and review. And those two selection processes then end up leading to the acceptance of the proposal, the selection of the proposal for funding. This is the point where the program officer usually calls the proposer, and it's a happy day. All of you who have had proposals funding know that's a real nice phone call to get, or email to get. Of course, we're stewards of the taxpayer dollars. So that means that after all of this technical and intellectual and broader impacts review has gone on, then we have to undergo some financial reviews. This involves interacting with, say, the sponsored research office at the university, the financial folks. And then finally, some funding goes to generally the university or whatever entity is performing the research. Of course, that's just getting the money out. Then the thing that we care about happens. Research and education. A group of students, a group of PIs, use those funds to push back the frontiers of understanding. So that research and education, uniquely across the board in support from NSF, is the final goal of all of this process. So this is the one data slide with some detail on it I want to show you. I want to show you what happens with the fund, what happens as a result of this review process. What I'm going to plot here is the cumulative amount of money, cumulative amount of funds that the foundation is obligating. And the positive numbers are funds awarded. The negative numbers are proposals that we declined. And I want to display those amounts, that cumulative amount. It's just going to grow as we go across the axes, versus the rating of the proposal. A proposal can be scored anywhere from excellent to poor, excellent and very good are really great scores. And even very strong proposals might score in between very good and good. So let's look at what happens. Let's look at the cumulative amount of money that goes out to various proposals as a function of their ranking. Well, this shows what you would expect. We start with the highest ranked proposals, and then the cumulative amount of money, the integral, grows as we go across and then becomes asymptotic at 3.5 or so. Notice the vertical axis. That's up to about $6 billion that's been funded in these data I'm showing you. What about the declines? What's that going to look like? Well, it actually starts at 5. There are some very highly rated proposals that we aren't able to fund. Let's think about the very good proposals, the ones that are ranked 4. Those proposals, any review panel will tell you, and any program officer will tell you, are excellent science. If we look at the proposals rated very good or better, that's $3 billion. That's $3 billion of excellent research that we're leaving on the table because we can't fund it. Of course, the other piece is there's going to be almost $6 billion of excellent research that we will fund. This is a measure of the funding that the National Science Foundation could easily deploy without making any changes to push the frontiers of research forward. If I were here with you in person, I would probably call for a show of hands or something to say how many people recognize this image. It's, of course, the first image of a black hole. It's the black hole at Messier in Messier 87. And this image was the focus of an announcement in a press conference on April 10th in 2019. Shortly after, let me talk a little bit about how the researchers obtained this image. This project is called the Event Horizon Telescope, and they obtained this remarkable image by using 7 radio telescopes spread around the globe. This is an image of the Atacama large millimeter submillimeter array that NSF funds in Chile. That was one of the telescopes that participated. But by synchronizing essentially the data from all 7 telescopes, the team was able to make a telescope, a radio telescope, the size of the planet. And then they were able to look at the black hole, the shadow of the black hole in Messier 87 with enough resolution to obtain this image. This image was very, very popular. This is a collage of newspapers that had the image on the front page the next day. When we first made up this collage, we left off the Washington Post. We went back and corrected it. We decided having the Washington Post on would be a good idea. But this image was so ubiquitous that a few days after it appeared, we were having Bring Your Daughters and Sons to Work Day at NSF. And the director asked a group of sort of 4 to 10-year-olds what this image was, and she held up the picture, and every one of them knew it was a black hole. It was really impressive to see how this idea and this concept had just permeated to everyone. This is the Daniel K. Inouway Solar Telescope. It was to be completed last summer until COVID-19 intervened, but it is just epsilon short of being finished right now. However, it is far enough along that they have been doing engineering runs and have seen the first light image on this solar telescope. This is a telescope looking at the sun with unprecedented resolution. This is the image from that first light, from that first engineering run. This is the highest resolution image of the surface of the sun ever taken. Each of the little cells that you see there is on the order of the size of Texas. And they are cells because they are regions over which rough thermodynamic equilibrium applies. That's a thermodynamic length scale for the sun. This image was so captivating, even though it's almost a practice image, that on January 30th, it appeared on the front page of the New York Times. There's a point here, and that is, images can convey science and capture people's imagination the way almost nothing else can. We are creatures who are designed to look at images. Speaking of images, here's another sort of piece of art. This is Kirigami, which is related to origami, but it's the Japanese art of paper cutting. And you can see 2 examples of Kirigami here. What does this have to do with things that the NSF funds? Well, it turns out Kirigami has to do with advanced manufacturing. We fund a lot of research in advanced manufacturing, say at engineering research centers or material science research centers that are inventing the next way we're going to make things and the next things we're going to make. And it turns out that the Engineering Research Center at Harvard MIT, the Materials Research and Engineering Center there, in this article, bio-inspired Kirigami metasurfaces as assistive shoe grips, and there you can see a reference to it, use these notions to create a shoe sole that flexes and acts almost like claws and has much better gripping capabilities. This is the kind of connection that creative people can make. Well, that image was interesting. All those images I think were interesting. What about image as a way of illustrating and seeing research? NSF for years ran the NSF Visualization Challenge. This is an image that won that challenge one year called Neurofest by Matteo Farinella. Look at that for a moment. You feel like you ought to take your colored pencils and color it in. Matteo Farinella is a neuroscientist turned cartoonist, and he wrote a graphic novel called Neurocomic about a man who falls into the brain. And this is the neuroforest that is, you can see the various structures that are familiar of synapses and all in the brain. I think this is a very striking image. This is another winner of the Visualization Challenge. This is a false color X-ray of a snapping turtle that Ted Kinsman from the Rochester Institute of Technology took. It turns out that he picked up this expired specimen on the side of the road one day. According to the commentary, his students were used to finding roadkill in the laboratory refrigerator. But he wanted to take an X-ray of snapping turtle, and when he did, he actually found that there were 30 eggs hidden inside this specimen. They're shown here in false color. I think it's a really striking image. A few people in the audience know about this image. This is an image of sea urchin biomineral crystals that, in fact, Poopa Gilbert here at the University of Wisconsin produced. Poopa's in the physics department. It's an interesting story in that most crystals of things like calcite have very smooth edges, but biomineral crystals have uncommon forms. And in fact, these are the calcite crystals from a sea urchin, a sea urchin's tooth, and each of the false color images there shows different regions of mineralization. So, I think that these kinds of visualizations, these kind of images that tell a story, are clearly part of the broader impact of science. But let me talk for just a couple of minutes about broader impacts beyond just the images that I've shown you. This is an image from Louise Charkoudian at Haverford College, and it's a very interesting story. You can see all of these bacterial plates that have different colors and different patterns having to do with the bacteria expressing different colored compounds. I'm a chemist, I have to put a couple of structures up, but these are the structures that are providing the colors that you're seeing on these plates. But it's an interesting story. This picture is from an article in PLOS Bio, and it is entitled Vibrant Symbiosis, Achieving Reciprocal Science Outreach Through Biological Art. Louise is a career award winner from NSF, and part of the broader impacts in her career project had to do with connecting students, chemistry undergraduates, and artists. But not just any artist. These are artists at a center near Haverford College for intellectually and developmentally disabled adults who are expressing themselves through art. They produced these remarkable images and inspired some of the pieces of art that you can see on the top left and top right. I commend her website to you. You find it at Haverford. It's a very interesting story and a very interesting article about what they accomplished. A real connection, a real broader impact that is connecting art, connecting science outreach, and connecting science with a unique community. Jessica Hoover is another career award winner at West Virginia University. She and some colleagues created something called the Community Engagement and in Science Through Art project. The goal was to educate and engage the community and introduce members of the community to the beauty of science. And here's one of their projects. It was to build a model of cytochrome C. This was the CESTA project in 2018. Starting with, you can see kind of their storyboard on the there on the left, where they were outlining what they were going to do. They built three-dimensional models. They molded structures, and then they created a large three-dimensional model of cytochrome C. The next year, they took on the brain complex, which in fact, as you can see in the second image from the left, involved some welding. They welded up the structures and finally created this large image that reflects some of the structures in the brain. So you've seen projects that were really sort of individual investigator kind of projects, but the National Science Foundation is the steward of the United States Antarctic Program. And one of the things that the National Science Foundation has done is to try to connect artists and writers to the Antarctic. If they get to Christchurch, we will provide the logistics for people who are selected for the program to be on the ice and to be able to execute some of their ideas. This is one of the ideas that Xavier Cortado executed. This is from a few years ago when that dome you see in the picture was in fact the South Pole Station that the NSF runs. It's now been replaced by a new, more elaborate, more modern structure. Over the years, the ice sheet moves. So if you put a pole in the ground, a stake in the ground, at the geographic South Pole, it won't be the geographic South Pole the next year. So what Xavier did was to put flags, 50 flags in place at the location of the geographic South Pole every year that humans had inhabited the South Pole. So over those 50 years, you can see how the geographic South Pole moved. When you visit Antarctica and go to the South Pole, there is a ceremonial South Pole where everybody has their picture taken, but there's also a marker that moves each year that indicates what is the real geographic South Pole. This is a book called The Edge of Physics. The author went to many different remote sites where physics are done. You're seeing it on the cover, a telescope in Chile, I believe. One of the places he went as part of the Antarctic Artists and Writers Program was to the South Pole when IceCube was being built. Now, some of you know that IceCube is the University of Wisconsin-led project to put strings of detectors in the ice to detect neutrinos coming through the Earth. This is in fact a picture of the building where IceCube, where the strings go down, where the detectors are housed. And this is one of the places he visited as part of the Antarctic Artists and Writers Program. George Steinmetz did a photography series in Antarctica. This is not a staged scene. This is people actually doing their work in Antarctica, which often involves tents and shovels. Well, a rather famous individual who spent time at the South Pole as part of the Artists and Writers Program was Werner Herzog. His documentary, Encounters at the End of the World, was nominated for an Academy Award as the Best Documentary Feature. And I like to think of Herzog here on the right, dressed up for some awards ceremony, and I picture him in the big red parka that everybody wears in Antarctica, and imagine that that's a more interesting way to be. Here's an example of something, they're shooting the documentary of people actually at McMurdo in Antarctica. Well, let me close by showing you images that I think are great. These are, of course, images of where we would all be if we were at the festival at WID. I love these pictures for a lot of reasons. You can see the Wisconsin Institute for Discovery. You can see the Capitol. And you can see that wonderful atrium. So I'm going to make a confession. 10 years ago, and I congratulate the Institute for Discovery on the 10th anniversary of the building. As it was being built, I was still at Wisconsin as an active faculty member then. I thought, well, this is going to be a lovely building, but it's not going to make any difference. And I was completely wrong. I have been so impressed at the way the Institute for Discovery has become a location for people on campus where events happen. It's an example of drawing people into science and bringing people together. So I congratulate everybody at the Institute for Discovery for all the wonderful things you're doing for the university and for science. So I will close by reminding you of NSF's mission: to promote the progress of science, to advance the national health, prosperity, and welfare, to secure the national defense. The National Science Foundation, we like to say, is where discoveries begin. We also like to say it's where discoverers begin, because one of the important things we do is help launch people into science. And that's one of the consequences of broader impact. So I'm really pleased to have been able to share some of these thoughts with you, and I look forward to answering any questions that you have. Thanks a lot.
Thank you so much, Dr. Crim. You can hear us all virtually applauding, as we would be doing if we were sitting in the town center at the Discovery Building. We're starting to get some questions coming in, and I'm going to use my privilege as the moderator to ask you one right out of the gate. I'm sure that given your time at Wisconsin, you're very familiar with the Wisconsin idea, which of course is our credo that we live by, that the work that we do at the university needs to impact everyone in Wisconsin and more recently the broader world. Is there a sense in which the broader impacts focus at NSF is sort of NSF's version of the Wisconsin idea for the benefit of the country? I wonder if you could speak to that and sort of why broader impacts and why all of the different ways that exist to address that requirement through the arts, through education, through technology commercialization. What is at the core of that you think is really special to NSF? Well,
I have always been enormously fond of the Wisconsin idea. I've always particularly liked the Wisconsin idea seminar where you haul a bunch of new faculty around the state, because I think that as we come from literally all over the world to be professors or faculty or staff at the University of Wisconsin, it's really important to realize what the reach of the university is. And you know, the original Wisconsin idea was the borders of the university or the borders of the state. And really now it's the borders of the world when you look at the number of international connections we have. So you're right in identifying that as part of the broader impacts idea, because broader impacts means we don't just think about pushing back the intellectual frontiers. We think about how it connects to people. We think about how it connects around the world. And the fact is, science is global. Science is global for a lot of reasons. Good ideas are not confined to a region. Talented people are not confined to a region. And if we're going to push back the frontiers, we're going to do it by being connected around the world. So this Wisconsin idea, which my colleagues from, Princeton or Berkeley or Michigan aren't as fond of my calling it the Wisconsin idea, but I think it's exactly what you said. I think it is in many respects a big component of broader impacts. Broader impacts, as you know, is more than just the first thing you think of. Oh, broader impacts is broadening participation. Well, that's not the question. It could be that, but that's not the only way you can do it. You can do it through some of the examples that I showed you. And so this notion of expanding the borders of our science around the world is really an important one. Great, thank you. And we've had a number of questions come in to follow up on some of the points you were making. And right out of the gate, picking up on where you just left off, is there room in NSF's view for art that is critical of science? Art that is critical of science, you say? Mm-hmm. I think that as scientists, we have to be intellectually honest, don't we? I just don't think we can be afraid of criticism. Mm-hmm. Every scientist knows that feeling of sending a paper into a journal and then getting a review back that's critical. and you get that review back and you're so angry. These people didn't understand what I was doing. And then you think about it. I used to always tell my coworkers that, let's go home and let's come back tomorrow and figure out why that person didn't understand us. Let's ask the question, could we be wrong? And so we have to be open to criticism. And I think all the vehicles for criticism, it isn't particularly fun to be criticized, particularly if you feel like it's unfair. It's part of intellectual honesty. Hey, I see from the chat that Francis Halzen's in the audience. So I'm so glad that that you did Ice Cube for us.
We had a question that wanted to go back, I think, to the turtle example. If you could say a little bit about what false color means in the X-ray image that you showed.
False color is just a way of, I said in my talk that we're visual creatures, right? And so false color is just a way of conveying, for example, intensity information or structural information, something that is different about two pieces of data that are in an image. And so we, for example, imagine that, that one had a much higher concentration of some species than the other. Maybe we would make the high concentrations blue and the low concentrations red. People are most familiar with this in terms of heat maps. Think of a weather map that shows you the south being very warm and red and the north being cool and blue. It isn't because the United States looks that way. It's because we have done false color to convey that information.
Thank you. You also, many of the images that you showed, one of the questioners posits that these are compelling examples of arts participation in the translation phase of research. Does NSF also support the integration of the arts into earlier phases of the science team research process, like conceptualization, development, implementation?
Very interesting comment, because I remember one time I was teaching general chemistry. I'm going to answer the question, but let me start back when I was teaching general chemistry. And a student came to me and said, you know, I'm a real visual learner, and I look at what the things you draw on the board and the formulas you write down and one thing and another, and I translate it into these sorts of images. And the student had a bunch of sketches, okay? And it was really interesting. What the student was doing was translating the thing that was on the board into something that spoke to her. I thought that was really interesting. So there are a lot of scientists that are very visually connected. Now, I wouldn't say that they would say, oh, we're going to use art to explain, to design our experiment. But the fact is, sketches that are metaphors for a cellular structure or for molecules interacting, for any number of things, actually actually they're the way we communicate. And it's often done at a level of abstraction. An enzyme docking might be a triangle and a piece that matches it. But it actually is using that conceptualization. The thing I don't think we do is to, unless it's an accident of our background, invoke much formal artistic training in that process. But I think that science is a very visual process.
And your answer is actually a perfect segue into this next question, asking if or in what ways does NSF collaborate with agencies that focus on the arts, such as the National Endowment for the Arts or the National Endowment for the Humanities?
So I am going to get this a little bit wrong, but let me say we have a memorandum of understanding with the National Endowment for the Arts, for example, and much of that plays out through our sponsoring things together in museums. That's one of the main ways it plays out. If the questioner will shoot me an email, I can arrange a more detailed answer.
And perhaps you'll provide your email in the chat as we're going, or maybe maybe your colleague Kim can.
Kim can put it up.
You could probably do that. Great. Similarly, is there a sense that in which NSF connects with the arts to explicitly link broader impacts with the UN Sustainable Development Goals? Is that something you might know about?
the sort of fundamental research that we support connects to issues that underpin notions of sustainability in a lot of different ways. Sustainability in manufacturing, sustainability in energy systems, sustainability writ large. I wouldn't say, and this is more my not having something on the top of my head about it, the connection to the UN program in particular. We do have a number of connections to the UN, but the connection to that particular program, I can't comment on, I'm sorry.
No problem. My friend and colleague Kevin Yimi is asking a question that I'm wondering about it as well, which is how effective is the structure of NSF and its relationship with the National Science Board in advocating Congress for research funding? And I'm wondering to what extent does broader impacts play a role in the relationship with Congress?
So that's two questions. The first one has a relatively simple answer. The second one is complex and important. The first part about what about advocacy or talking with Congress, we answer questions from Congress. We tell Congress what directions we're going and what we're up to, and we respond to, like I said, queries, but also directives from Congress. But as a federal agency, the National Science Foundation does not go and advocate or lobby Congress. We are not to do that. The National Science Board is in a different position. It's an advisory board. It advises Congress and the President, as well as overseeing NSF. And the members of that board act differently and often carry the case for NSF in ways that federal officials cannot. The second part was about how does broader impacts help us with Congress? It is critical to think about translation. When we can go tell the story of having funded research into thermophiles in Yellowstone, and that turned into PCR, okay? That's a great story. When we talk about funding the digital library and that turns into Google, that's a great story. When we talk about funding studies of fluorescence in jellyfish, and that turns into green fluorescent protein, which is critical for cancer research, that's a great story. Those are examples of translation that really are broader impacts. Now, one of the challenges we have is that broader impacts of what we do usually don't play out in 3 to 5 years. They often play out on a longer time scale, and it's really important for us to have the institutional memory to make those connections and to look back. Okay.
Another question relating to high-level government initiatives. Can you say anything about the new bipartisan $100 billion Endless Frontier Act, and if NSF will be the administrator, and who and how can we support its passage in Congress?
Let me give you an answer that you won't like, and then an answer you will, I hope. The answer you won't like is, I cannot comment on pending legislation, okay? The more relevant answer is the ideas behind the Endless Frontier Act are very, very important, and they are things that we are thinking about a lot. They have to do with funding basic curiosity research and driving its translation, just as we were talking earlier, into various sorts of outcomes. That's really important for us to be able to do. And so the ideas of the Endless Frontier Act, the idea of partnerships, the ideas of innovation, the ideas of translation, the ideas of funding more curiosity-driven fundamental research that seeds all of those things are really attractive ideas. They're ideas we talk about all the time at the foundation, and they're really what we're looking to do. But I cannot comment in particular about that legislation.
Understood. A researcher on campus, David Gagnon, is asking, he's mentioning that his lab produces broader impacts educational video games for a number of NSF funded groups like MRSEC and IceCube. And he's wondering what are the best opportunities for connecting with more PIs and even coordinating broader impacts across many PIs?
That's an excellent thing for us to be thinking about. Our Office of Legislative and Public Affairs, in many respects, is the nexus for a lot of these things. But what you're really saying is, why don't we have a broader impacts conference associated with NSF broader impacts? There are organizations like ARIS that do work in the area of promoting broader impacts, and we in fact fund some of those organizations. But that's an interesting suggestion. I'm glad to hear that suggestion. Let me talk with some folks about it.
And Dana Aiton Schrenker is wondering if you can give examples of collaborative funding partnerships that you've had or would want to have with private philanthropy for arts and science connections.
We have developed more connections to philanthropies in the last few years than we've had before. The BREAD project with the Gates Foundation, with the Simons Foundation, we're funding some math bio research institutes. But I don't believe most of the philanthropies interested in supporting arts realize that there might be connections to make with us. Mm-hmm. So that's, if the questioner has ideas about building those connections, I promise you that partnerships are something we are really open to and really interested in right now.
Great. I'm not sure you're going to be able to speak to this next question, but Kevin Hamilton is wondering how NSF is reckoning with the terms of the recent executive order on combating race and sex stereotyping. He says that many of us are concerned that this order's terms stand to constrain our aspirations for broader impacts and more when working with federal agencies.
Well, of course, it potentially, if interpreted narrowly or incorrectly, could have a lot of impact on particularly our broadening participation efforts, our efforts to drive diversity and inclusion. I'm going to digress for a second and then come back to answer that question. Why do we want a more diverse workforce? Why do we want more people from different backgrounds in science? Partly it enriches science. There's a lot of good data that say you do better science with a more diverse group. But there's a more important point. And that is, if we are going to have the scientists that we are going to need, we are going to have to draw on all of our population, not just the traditional part of our population. Now, let me go back to the executive order. The executive order says something very important. It says that we are supposed to continue working to promote diversity and inclusion and continue training associated with diversity and inclusion. An executive order for a federal agency has the authority of law. We will obey, we will conform to the executive order. On the other hand, the executive order tells us to continue what we're doing in terms of increasing diversity and inclusion, and we will continue to do that. Okay? So I understand that there's a lot of concern about it. I think we need to let this play out. So our first reporting requirements aren't until November 20th or something like that. And I think we need to let this propagate and understand what the detailed instructions we're going to have, the detailed guidance we're going to have. And I think people need to be alert to what the consequences could be. But I also think it's important to interpret, to think about the very positive message that we want to continue working on diversity and inclusion.
Great, thank you. Pupa Gilbert, who is in the audience, thanks you for showing her work and is wondering if you know of any case in which art inspired science discovery.
Pupa, you probably know better than I. Has to be. I don't know if but your question was, do I know of it? You know, there's a famous story. There are several stories about people having dreams and having a scientific revelation. The dream that led to the structure of benzene, supposedly by Kekulé. So I feel like everything that drives our imagination has to drive our science. And so there have to be a ton of them. I'm sorry, I don't have one for you right now, Poopa. Poopa may have one and she'll put it in the chat.
That'd be great. One of the organizers of A2RU, Mary Rose Flanagan, is asking how long has the broader impacts component been in place, and what has been learned, and how have the guidelines evolved from what, based on what's been learned over time?
Broader impacts has been a criteria for more than a decade. Certainly, probably 12 or 15 years. It has evolved quite a bit. Not so much the words as people's understanding of what it means. For example, can the broader impact be the translation of your science? Can it be you're creating a piece of science that influences other pieces of science? Most people think it does, but folks have also tried to look at broader impacts, if I can say this more broadly now, in thinking of how we can really do imaginative things. Broader impacts, which is treated in variable ways by different disciplines, could be an opportunity for folks to do things that they needed the nudge to do or needed the opportunity to do. But it's certainly the case that the articulation of broader impacts has grown over the years, in that people have become more and more, are realizing they need to think about it more and not just simply sort of check a box. One other thing about broader impacts that I would like to see happen, and this is an evolution in broader impacts. If you have a whole collection of investigators at a major research university like Wisconsin doing broader impacts, perhaps they're doing broader impacts together, the university providing some structure that would help drive broader impacts. And there are programs like the Delta program at Wisconsin that have done some of those kinds of things. I think something like WID, I think the Institute for Discovery could be driving collective broader impacts. If you can have a bunch of smart people who feel like they want to have a broader impact component to their proposal, perhaps they're doing something collectively would be much more powerful. I think it could also be easier and less frustrating to people. So I'm calling on the leaders at my university to think about how we might facilitate that.
And just we're running out of time. There are a few questions that we won't be able to get to, but one that I think dovetails nicely with what you were just talking about is there a sense at NSF that broader impacts can impact policy and help inform policy?
Oh, very much so. We have people who, well, let me back up. Science, facts, science, research should be a lot of what goes into policy. Now, policy gets made not just by scientists, it gets made by elected officials and other folks with other kinds of expertise. But as scientists, as researchers, we can provide the data that are critical to making that policy. So when you think about the broader impact of a piece of research, one of the things to think about is, will this feed into the policy discussion? Will this help a policymaker understand something, make a decision? That's a powerful broader impact. I would like to see the policy consequences of broader impacts become really popular, because it's a way for us to translate, if I can say that, our basic research into something that is going to matter to the entire nation and to the entire world.
That seems like a really good point on which to end, and we're just about out of time, so I apologize to those of you who asked questions that we couldn't get to. And again, I want to offer virtual applause on behalf of all of us. Thank you so much, Dr. Crim, for your thoughts, for your excellent presentation, and for making time to celebrate the Science Festival and A2RU with us. Thank you so much, and be well, stay safe, and safe virtual travels back to DC.
Thank you very much, and congratulations to the Institute for Discovery on its anniversary, and for this wonderful festival and this wonderful event. I'm glad I got to participate. I'm just sorry I didn't get to see everybody's smiling faces. So thank you very much.